How physics shapes your world and messes up your movies with Andrews Menek. Let's start with something you already feel. Newton's third law. For every action, there's an equal and opposite reaction. This is the principle behind rocket propulsion, swimming, and even recoil from a gun. No matter the situation, if you exert force, you're getting one back, whether you like it or not. Let's break it down. Force equals mass times acceleration. So if I push with 50 newtons, the wall pushes back with exactly 50 newtons, but in the opposite direction. Equal, opposite, every time. Now let's talk about momentum. Momentum is an object's mass times its velocity. In a closed system, that total momentum is always conserved. Here's a simple example using pool balls. The white ball strikes a stationary ball. After the collision, the white ball slows down and the red one rolls away. That motion isn't random. It's momentum being transferred. All the momentum from the white ball moves into the red ball, just like the law says. The total momentum stays the same, it's just shared differently between the two after they collide. We also see momentum in action during car crashes, football tackles, and bumper cars. Engineers rely on this principle to design systems that absorb and redirect energy safely, because momentum can't be stopped, only redirected. Let's break this down with numbers. Imagine a 2 kilogram object moving at 3 meters per second. That gives us 6 kilogram meters per second of momentum. Now it collides with a 1 kilogram object, and they stick together. After the collision, they both move at 2 meters per second. That's 2 kilograms plus 1 kilogram times 2 meters per second, which also equals 6. Different speeds, different setup, same total momentum. That's the law in action. Momentum before equals momentum after. Next, let's talk about light, and why it bends. When light moves from one material to another, like from air to water, it changes speed. And when the speed changes, the direction changes too. That bending is what we call refraction. Here's a classic example, and one that really got to me when I was a kid. A straw in a glass of water. It looks bent or broken, but it's not. What you're really seeing is light bending as it travels from the water into the air, changing the way your brain interprets the image. So why does light bend when it hits water? That's where Snell's law comes in. It's a formula that helps us figure out exactly how much the light will bend. Every material has something called an index of refraction. Air is about 1, water is around 1.33. The bigger the difference between the two materials, the more the light bends. Snell's law uses those numbers and the angle the light hits at to calculate the path the light takes when it crosses the boundary. That's how we can predict why a straw looks broken, or how to design lenses and glasses that work just right. Refraction isn't just a cool science trick. It's the reason a lot of our technology works. Eyeglasses bend light to help people see clearly by focusing it right onto the retina. Camera lenses do the same thing, capturing sharp images by guiding the light onto a sensor. And fiber optic cables, light bends and reflects through tiny glass strands carrying data across cities in milliseconds. Refractions makes all of this possible. But sometimes, movies ignore how light really works. In Aquaman and other underwater movies, everything looks crystal clear, like it was shot in a swimming pool. It looks cool, sure, but it doesn't follow the rules of physics. Here's what's actually happening. Underwater, light scatters, colors fade, everything blurs, and distance becomes hard to judge. But in movies, somehow people can see perfectly. That's not how light travels through water, and definitely not how we experience it. If they showed it realistically, underwater scenes would look darker, fuzzier, and full of distortion. You'd lose detail, and things in the distance would almost disappear. But hey, it's a superhero movie. I guess they're bending more than just light. So here's the big picture. Push against something, it pushes back. Smash into something, it shares momentum. Look through something, Light bends and tricks your eyes. It's all physics, whether we notice it or not. Thanks for watching. I hope you see the world a little differently now, because physics is everywhere, and sometimes it's even cooler than the movies.